So in thermodynamics, when we're studying that, we want to do it quantitatively. So you might imagine doing that in an open system, but that's going to be difficult, right? So if I have this reaction occurring, maybe I put the hydrogen and the oxygen in here, and I want them to combine together and make water. If I'm studying that and I want to quantify it, maybe I think this is a good reaction to use for the new generation of vehicles that are going to run on hydrogen gas instead of petroleum. So I want to know, how much energy can I get from this reaction? Is it going to be feasible? Can I make a gas tank that can hold enough hydrogen to do this reaction enough so people can go on long trips? I want to quantify how much energy is going to be associated with this reaction. If I do it in an open system, that's not going to work too well. So what we just saw on the previous slide was this particular reaction, because these bonds don't take much energy to break, but the new bonds release the net energy, this particular reaction will release energy into the surrounding. If I want to quantify how much that is, I need to capture that energy so I can measure how much it is. But if I have an open system and the energy just escapes, and if molecules can also evaporate and escape, now I'm not doing that in a careful way. And I'm not able to capture the energy. I really can't quantify it. A closed system is better because at least now I don't have any water escaping. I've sealed that off. But still, if heat can be exchanged between the system and the room, then that heat just distributes through the room. I don't know how much heat it is. So when we do these reactions quantitatively, we want to use an insulated or isolated system. So now, when this reaction occurs, and I'm producing energy, or energy is released, so the potential energy comes out. This has more potential energy, this has less potential energy. That potential energy gets converted into kinetic energy. It's released from the reaction. Where does it go? I can't escape the flask, so it stays. I've captured it. An isolated system will capture that energy, keep it in there, and that will cause a temperature increase because of the increase in kinetic energy. So if I jam a thermometer in there and I measure how much the temperature is increasing, then I can quantify how much the kinetic energy is increasing, and I will know how much potential energy the reaction released. So I can quantify that. So generally you want to work with an isolated system as much as possible. And that is also called a calorimeter, which makes sense because it's a meter and it's measuring quantitatively how many calories are being, or how much energy is being released or absorbed in the reaction. A couple more important details. We've mentioned this already, but this is just a recall that the law of conservation of energy is the first law of thermodynamics. So it says that energy can't be created or destroyed. So if the system has an increase in energy, the surroundings must have a decrease in energy by the exact same quantity, so that the total change in energy is zero. I'm not creating energy. I don't have a net increase in energy or decrease in energy. The system can have a net increase in energy, which would be endothermic, or decrease in energy, which would be exothermic. But whatever energy change the system undergoes, the surroundings must undergo the same energy change with the opposite sign to absorb any energy the system is releasing, or release any energy the system is absorbing. So that's just the law, the first law of thermodynamics. Then if you are looking maybe just at the system, it can have an overall energy change as long as the surroundings has a corresponding energy change, so there's no net change in the universe. The system's energy change overall, its internal energy, is dependent upon the heat change for it and also work. So normally in chemistry we're not really dealing with work too much, because if we just have a container, there's a reaction, and the reaction releases or absorbs energy that's usually just given off in the form of heat. Work is done when an object with mass is moved some distance. Usually our reactions don't do that. Sometimes they do, though. That happens in your car. You have gasoline in your tank. The gasoline is burned by your car. Initially, you need some energy to break the bonds up in the gasoline. But then when new bonds form, when it combines with oxygen, it forms CO2 and water. A lot more energy is released because that's more stable and lower in potential energy. So that energy is released. Some of it's released in the form of heat. That's why your engine gets hot. Some of that energy is released in the form of work because it moves the mass of your car over some distance. So your car is designed to take as much of that energy released as possible and convert it to work. Any energy that's released in the form of heat is wasted because then that gas was burned and your car hasn't moved at all. But when you do work, you can move an object. So the total energy change is the combination of the work and the heat. So this slide illustrates a couple different possibilities. So you might have on the first one here, you might have a reaction where all the energy released is heat, and that heat would just be escaping, and it would go into the surroundings. The heat of the surroundings would go up. You might have a situation where work is done instead. So if some of that energy, instead of being converted into heat, is converted to work, the work could push or expand a gas or something and push that piston up. That's what happens in your car, right? There's pistons that drive the motion of your wheels, and so the expansion of that piston is what causes the work to be done. So you're pushing that object at some distance. So a system could release heat or release work. So from the point of view of the system, this is energy that the system is releasing. Whether it's releasing heat or doing work, that energy that the system no longer has, it's done that energy on the surroundings or push that energy into the surroundings. So it can lose energy in the form of heat or work, or it can gain energy in the form of heat or work. Right? So if you have a gas and you have some outside force compress that gas into a smaller volume, you are doing work. And that energy is going into the system because now there's more potential energy for that gas to re-expand and equilibrate back to a lower pressure, right? And you experienced that when you did lap 5. And you had that little syringe. If you pressed in the syringe and then you released, the syringe would pop back out a little bit, right? Because you were doing work on that gas that was in that syringe. You were doing work on it. It was absorbing that energy and compressing it down. You're pushing the gas into a smaller volume, doing work on the gas. You're pushing the objects with mass into a smaller space. So you were doing work on the gas, so the gas is absorbing that energy from that. So from that point of view, if you do work on an object, it's a positive change in energy because the object is gaining that energy. And if you put heat into an object, you put it on a hot plate or whatever, heat it up, that's also energy that the object is absorbing. So this slide is just showing you, again, we're looking at it from the point of view of the object, the system, or the chemicals. If you put heat in or do work on it, that's positive change in energy. If it releases that heat or does work itself, then that's negative from the point of view of the system. So let's look at a quantitative example of that. So here we have worked example 10.1. It tells you that I want you to calculate the overall change in internal energy. So that's going to be equal to any change in work plus any change in heat, which is represented with the Q. I'm not sure why. So it says the system absorbs heat. So the number I plug in is 188 joules. Should it be positive or negative? Should be positive. From the system's point of view, if it's absorbing it, that's a positive quantity. Then it says that the system does work. Is that positive or negative? Well, it might be positive for you because then you don't have to do the work if the system is doing the work. But we're not looking at it from your point of view. We're looking at it from the point of view of the system always. So from the system of the point of view of the system, it has to do that work. It's using energy that it had to do work. It doesn't have that energy anymore. So that's a negative change in energy for the system. So then I add 188 minus 141, and I get 47 joules net overall. That's the overall change in energy for the system. So it is absorbing more than it is releasing, but it's not that much. Another example that's very similar, look at 10.10. So here it says a gas expansion, 87 joules of heat is absorbed from the surroundings. So here we want to calculate the work done. We're looking to calculate the work. So they're giving us the fact that 87 joules of heat is absorbed. So that's a positive quantity. This is 10.10. And then it says the energy of the system decreases by 128 joules. So if the energy is decreasing, that's a negative. Total, as they're telling us, the total energy is decreasing. The total energy change is negative. So if I'm solving for work, the amount of work energy associated with that, I'd have to subtract 87 from both sides. That would cancel. And the change in work energy would be negative 215 joules. So in order for a system to absorb 87 joules and have a net change of 128 joules, it has to do 215 total joules of work. Questions about that? Another one, 1012 asks you to calculate the heat change for a system. And in that one, they're giving you that it's doing work on the surroundings equal to 67 joules. So if it's doing work, that's a negative. And it says the total energy change is negative 213. So if I want to solve for heat, I can add 64 joules to both sides. So that will cancel. And I'll have the heat equals 64 minus 213. And that would be negative 149. So it's the heat that's being lost from the system would be negative 149 joules. Any questions about that? So let's look at a couple of the other ones here. 10.2, what is heat? Heat involves both the kinetic energy and potential energy change for a system. So you want to keep in mind it's both of those. How does heat differ from thermal energy? Thermal energy usually refers to kinetic energy. Right? That's energy you can observe changes in by measuring temperature changes. So heat also includes potential energy for chemicals and substances. Under what condition is heat transferred from one system to another? Well, it's a little bit tricky because since heat involves both kinetic energy and potential energy, we have to think about both of those. So if I'm going to transfer heat from the system to the surroundings or vice versa, that could involve a kinetic energy change or a potential energy change. So how would the kinetic energy be transferred from one object to another? So when you're breaking and forming bonds, that's the potential energy. So if you break and form bonds, then that changes the stability of the electrons and how close they are to nuclei. That's a change in potential energy. So when you change the potential energy, that energy will be transferred between the system and the surrounding. The potential energy may be converted into kinetic energy, so you may see a kinetic energy change for the surroundings if the system undergoes a potential energy change, so that's also important. Usually what we see is the potential energy change for the system gets converted into a kinetic energy change for the surrounding. What if we already have the energy in the form of kinetic energy and we want to transfer that kinetic energy from one object to another? What has to happen? Yeah, collision. Right, you've got a high kinetic energy, fast-moving particle. For it to transfer its motion or kinetic energy to another particle, it has to collide, and that collision will allow the faster-moving particle to transfer its energy to the slower-moving particle. 10.3, just to remind you that energy comes in multiple forms. Chemical energy is a form of potential energy, right? So chemical energy is energy that could be released if the bonds were rearranged or the electrons were rearranged into a more stable form, so that's potential energy. Heat includes both potential and kinetic. Light is its own form of energy. We talked about that. It's waves or packets of energy called photons that travel through space, through a vacuum, or through objects. Mechanical energy is more potential energy, like you might have a spring that's been stretched, and now that has the potential energy to snap back. And electrical energy as well is another form of potential energy, like a battery or an outlet. There are electrons that are not held very strongly to whatever they're attracted to begin with in a battery, and so they have the potential to go through a wire through your electronic device back to the other side of the battery where they could be more stable. And so that motion of electricity is tricky because if before you connect the battery to your device, there's the potential for electrons to flow. There's a potential for energy. Once you connect it, though, now you have flowing electrons. That's motion, so that's more like kinetic energy. Then 10.7 says decomposition reactions are usually endothermic. Why is that? Right, we're breaking bonds, right? Decomposition is where one molecule breaks down into a smaller number of molecules. So in a decomposition reaction, usually you're breaking more bonds than you are forming. And since breaking bonds always requires the system to absorb energy to overcome attractions, that will probably be more positive overall than negative for the system. And so likewise, combination reactions are usually exothermic, right? Because combination reactions where you take multiple things, you combine them into one thing. So in that case, you're usually forming more bonds than you're breaking. And when you form bonds, you're decreasing the potential energy, so energy is released. And so that exothermic energy is going out of the system.